And hello, welcome. Today we're going to talk about turbulence modeling, and in the last video we just did some evaluation of comparing aiding mixed convection for some dynamic Smagorinsky models. These are purely LES models, and today we want to talk about, well, since we already compared with DNS data, we also want to compare it with experimental data. Of course, the difference between DNS and experimental data is, of course, we have a very good, we can be sure that this data is real for instance, but DNS data, you tend to get more detailed information because you can measure the turbulence statistics very accurately, and you can measure with almost all the precision you want. Whereas for experimental data, you cannot measure all of these turbulence statistics and for example, the temperature profile and the velocity profile with infinite precision. But it's always good because it shows you what the real life situation is, and you don't really have to validate any of it. You just have to be aware of the experimental errors you may get from measuring the temperature and the velocity. So for experimental data in mixed convection, we have the heating, ventilation, air conditioning case by this Chen Qingyan in this HVAC. So the dynamic Smagorinsky model was compared against experimental data in a 1 meter-ish by 1 meter-ish by 0.7 meter room. The sidewall temperature is 15, floor temperature is 35. The mesh is 62 for this, 62 for this, and 12 for this, 62 by 62 by 12. So alright, so what are the typical errors? Alright, for example, if the experimental data shows a 20 degrees air temperature, the dynamic Smagorinsky will predict a 21 degrees. So is this like a 5 degrees temperature difference? Because we take this 20 degrees as a reference, well, we can use that. Okay, but well, when you try and measure errors, you also have to be aware of where your reference temperature is. For example, if you were to use Kelvin, then you would say this 20 degrees and 21 degrees is super close, right? Alright, so let's say you try and measure this temperature difference using Kelvin. So what will you get? You get 1, okay, so 1 Kelvin temperature difference. Then you divide by 273 plus 20. Then we will get a very, very small temperature difference percentage. Alright, so okay, equals 1 divided by 293, for example. Then you get an error of 0.3%. So which is correct? Which is correct? Do we use 5% or 0.3%? Okay, so to eliminate some discrepancy, you could say this. All right, the relevant temperature scale. The relevant temperature scale is it's actually, maybe you can say the Tmax minus Tmin. So Tmax is actually 35 degrees at the floor. Tmin is actually 15 degrees. So this is 20 degrees, whether you use the Kelvin scale or the centigrade scale or Celsius scale. So 5% would be closer to correct. Why am I saying this? Because sometimes it's very difficult to get this to get this error measurements, especially when the measurements themselves are almost zero. What do I mean by that? So let me get my paint out. Okay, so I get my trusty paint. Okay, so we have a situation like this. All right, for example, you have a natural convection case, and then all right, let's say you have a hot wall and you have a cold wall. Yeah, so your velocity profile is going to be something like this. So you have a hot wall and a cold wall, and let's say your hot wall, you of course have you have to specify gravity. Okay, so gravity is this way. So in the natural convection case, your velocity profile will be something like this. You have a big bump there, and then the cold wall you have this big bump here. Okay, so what actually happens? All right, if this is like so-called infinite plate, and then yeah, you have this hot and cold. So this is the velocity profile in the y direction. All right, so you have this velocity profile, and let's say you look at one of the values here, and this is actually, for example, 0.01 meters a second. All right, and let's say your LES model gives you 0.015 meters per second. Okay, if this is the case, and you were to say, okay, the error is like this, 0.005. Okay, so you subtract these two, divide by 0.01, and then this will actually amount to 50% error. Okay, is this 50% error correct? All right, is this 50% error correct? So yeah, the tricky thing is because we have this this value very close to zero. If let's say you were to take the same measurement here, and the error here is also 0.05 or 0.005 meters per second, and then your speed here is 1 meter a second, and what is your error like? Your error here is more like 0.5%, right? It's about 100 times smaller, just by virtue of where this thing is. So yeah, it's a little bit difficult because of this problem where you have, like, negative velocities and velocities very close to zero, but they have this kind of problem. Okay, so for fluctuations like this, because you have this kind of velocity scales, okay, that go very close to zero or very close to negative. All right, and then sometimes if let's say you have again a velocity here, it's supposed to be 0 meters a second in the DNS, and then you have 0.01 meter a second in your LES simulation or whatever else. Then what is your error going to be? Infinity? Well, that makes the LES simulation look really bad. But in fact, if you have the trend line, if you have your LES curve, something like this, and then you have more or less the same trend line, right? You have more or less the same trend line, but just because the data point is so close to here, your error goes to infinity. Is that representative of how inaccurate the LES simulation is for this purpose? Right? You just want a rough velocity profile, and you want your values near the wall to be more or less close to what it should be. I would say not so much. I don't think this way of measuring error is really representative of how accurate or inaccurate this LES simulation is. You can see the hypothetical LES simulation is very, very close. If this blue curve is very, very close to the green curve, which is DNS, we take the green curve to be DNS, then I'd say this is not the best way. I would actually say that maybe let's have it this way. We have representative velocity scale at the bottom. Maybe we have Umax minus Umin. Alright, you have Umax minus Umin. Then you can take the error, alright, the error or the error time, okay, percentage. You have a percentage error here, percentage error. Then maybe you have the actual error, the actual what do you call that, delta E, actual error, your deviation from what it actually is. So for example, if it's close to here, it will be 0.005. Okay, 0.005. Then maybe you times 2 because you can scale it according to the difference between here and here, or you can, or the other way to think of it is your characteristic velocity scale. Characteristic velocity scale will be U max minus U min over 2. So I mean the 2 is pretty arbitrary here. It depends on whether you want to use like this velocity scale from here to here, or rather let's use blue, from here to here and from here to here. Okay, do you want to use this velocity scale here or this velocity scale here to measure error? Okay, so that's something just to be mindful of when you do your error measurements. So again, it shows here for more real case, experimental data shows 0.25 meters a second, LES shows 0.20 meters per second. Depending on how you look at it, the error can be 20% off, which is huge. Okay, but if you take a look at the U max and the U min, okay, U max is actually 0.25, U min is minus 0.25. Okay, from this experimental data set. So you have a situation that looks something like this, where the U max is actually 0.25 here, and the U min is actually minus 0.25. Okay, so you have this same kind of situation, and the largest error, I mean your typical or largest error, will be this much, and then maybe this is your characteristic velocity scale, and LES will show 0.05 meters a second deviation. So I would say from this calculation, your error percentage is maybe 10%. It's 0.05 or 0.25 minus 0.20 over 0.5. That will give you about 10% error. In my view, the agreement is pretty decent. It's reasonably decent for this application, especially since your main concern is temperature fluctuations. It just so happens that, of course, if you were measuring against a 20 degrees C temperature, 5% temperature difference would be the same whether you use this or this Tmax minus Tmin method. And I prefer the Tmax minus Tmin method. It is more consistent across all the temperature scales, and likewise for velocity. Okay. Yeah, likewise for velocity. So this is how I prefer to do error measurements. Okay, so agreement is decent here in your T and U profiles, and though for turbulence statistics it's much harder to match. In some cases it's as much as 20 or 40% off. Okay, so this is for mixed convection. But mostly it's like natural convection here. There's a lot of natural convection as compared to the forced convection. Okay, natural convection is more dominant. Okay, so we can move on to opposing mixed convection, but before that I want to pause for a while, and then I'll say, okay, in mixed convection you have these few situations, right? You have let's say you have a spectrum of, let's say you have U versus Y, and then okay, you will have, okay, maybe I'll just shorten this. I don't want to spend too much time here. Alright, let's see. I'll use this spectrum. You have a spectrum, right, in mixed convection. Okay, you have mixed convection, and you have a spectrum, right? On maybe the left you have natural, on the right you have forced. Okay, so your mixed convection can be somewhere in between this natural and the forced. How are you going to say, let's say over here, if you have a flow here which is mostly natural convection, mostly natural, and here where you have mostly forced, Okay, how are you going to quantify this, right? Are these flows the same? First question, are these flows the same? These flows are definitely not going to be the same. So this is not going to be the same. How then are you going to quantify how much natural convection is versus forced convection? Well, there are two very important numbers for natural convection and forced convection. For the natural convection is a Grashof number. For the forced convection we have the Reynolds number. And okay, so if you were to compare, let's say you were to have a ratio between these two. You want to have a ratio. Okay, you want to have a ratio of the Grashof. Grashof is like the so-called relative inertial, okay, natural convection forces over viscous, okay, over the viscous forces. Okay, this is, of course, you actually square this because you have a new square term in the denominator for your Grashof number. Reynolds number is you have an inertial force over viscous, right? So if you want a ratio between these two, you need to you kind of need to have a Reynolds number squared. You need to compare Grashof against Reynolds number squared rather than Grashof against Reynolds number, because the viscous forces, they are squared in the Grashof number denominator and they are to the power of 1 in the Reynolds number denominator. So if you want to find a ratio between both of them, let's say the ratio of natural convection to the forced convection, you would use this dimensionless number, and this is actually called the Richardson number. Okay, the Richardson number. So this is the ratio of forced or natural to forced convection forces. Okay, pardon the handwriting, but okay, hopefully you get the idea. It's a ratio of natural to forced convection. Okay, natural to forced convection. So what are the typical ranges of this? So if you have natural convection, you have a Richardson number more than 10. Okay, and then you can sort of neglect the forced convection bit. You can sort of neglect the forced convection bit in this case. And then in the other end of the spectrum, you have Richardson number less than 0.1. Okay, then you can neglect the natural convection. Okay, you can neglect the natural convection for the most part. Okay, when I say neglect, is probably more to do with the velocity profiles. You would see later in the simulations that even a small little bit of natural convection in a turbulent forced convection flow will actually severely change the heat transfer coefficient and even the skin friction coefficient. We'll see that in a while. And of course here you have the in-betweens where you cannot neglect either bit. Okay, so this is the Richardson number. Just want to either refresh your memory or just introduce it to you over here. It's a very important number. So okay, so we want to move on to opposing mixed convection, right? So opposing mixed convection is where the natural convection and the forced convection go opposite each other. And what is the typical Richardson number? We shall see in a bit. And this paper actually comes from Ding et al., Ding and Company, 2020. And what they do is to compare this friction Reynolds number and the Nusselt number, okay, for a fixed Richardson number. Okay, the Richardson number here is about 0.048, sorry, 0.048. So for all intents and purposes, most of the time you can neglect natural convection here, but when you have this mixed convection heat transfer, we can't even we will notice that we cannot avoid we cannot neglect this natural convection in this case, because it affects our Nusselt number a lot. So what they do is to compare this friction Reynolds number and the Nusselt number. And friction Reynolds number is something you would see very, very often in turbulence literature. It is different from your regular Reynolds number. And instead of using U mean here is U mean here is replaced by U tau, which is the friction velocity. That's why it's called the friction Reynolds number. Okay, so yeah, hopefully this video actually just goes through some experimental data comparison and the Richardson number again. Okay, so this is very important for turbulent mixed convection. So let's stop here. I'll elaborate more on this friction Reynolds number in the next video, and I'll go through some of the results of this paper where they actually tested the Yeoh model for mixed convection of air. So that's compared against DNS data, and yeah, I'll stop for now. Thanks for watching. I'll see you guys next time. Bye bye.